On Monday, September 26th, at 7:14 p.m. Eastern Time, NASA successfully crashed their DART spacecraft into an asteroid in an attempt to change its course. The goal of the mission was to determine if a spacecraft could be used to alter the trajectory of an asteroid, which would have significant implications for planetary defense. And thankfully, we were able to witness this historic event live on the agency's live stream. The Double Asteroid Redirection Test, or DART, launched from Vandenberg Space Force Base in California last November and took 10 months to reach its target, the asteroid Didymos. As it approached, the 530-mile-per-hour impact shook the small probe, sending back telemetry data that will help scientists learn more about asteroids. Here is what we know so far. So the most important thing, did it work? Well, yes. Didymos is actually a binary asteroid system consisting of a large rock about 7.5 miles across and a smaller moonlet about 5 miles away, orbiting it every 11 hours. And the DART team wanted to test on the smaller one. But how do you move an asteroid? There are a few ways you could theoretically nudge an asteroid off its course. One is a gravity tractor, where a spacecraft would basically sit next to the asteroid and use its own gravity to pull the space rock in a different direction. Another option is a more direct approach, like smashing a spacecraft into the asteroid. Gravity tractors are cool and all, but they take a long time, and so NASA went with the smash method for this first test. DART was only about 7 million miles from Earth when it reached the asteroid, making it the closest spacecraft ever to an asteroid at that point in time. After crashing into Dimorphos, the moonlet, NASA believes that it changed the orbit by about 32 minutes, shaving an hour off the total orbital period. That might not sound like much, but considering that Dimorphos is traveling around its primary at roughly 14 miles per second, 32 minutes is a really big deal. Basically, it worked way better than they expected it to. In a press conference after the event, NASA officials called the mission a success. And who knows, maybe we'll actually end up using this as a real defense mechanism against incoming killer asteroids. But why this asteroid? Why did they choose Didymos? Well, there were two main reasons. For one, it's relatively close to Earth. It orbits the Sun every 2.3 years and has an aphelion, or farthest distance from the Sun, of just over 1.2 astronomical units, meaning it comes closer to us than many other asteroids out there. The second reason is because it's a binary system. Most asteroids out there are single objects, but about 15% of them are in systems like this. And studying a binary gives you more information than you would get from a single asteroid. Plus, the smaller rock is only about 7 million miles from Earth at its closest, making it much easier to observe than most targets would be. So when exactly did the crash happen? Because NASA kept showing this graphic of the two asteroids with the little yellow line between them, which I assumed represented time, but I wasn't sure. So let me break that down for you. This shows the ground track of the spacecraft in blue and the asteroid in yellow. The time is listed in Universal Coordinated Time, so UTC, and each tick mark represents 1 hour. You can see that on September 26th before impact, the two lines are very close together. They become one line as the spacecraft reaches the asteroid and crashes into it. This is because the camera can't distinguish between the two anymore once they get so close. Before the impact, the lines appear to cross several times, but this isn't really crossing in space. Instead, it's crossing on our 2D screen because the camera is getting a view of the asteroid that's partially behind the spacecraft. That's why the asteroid appears to turn slightly over the course of a few hours before going off camera. If you want to watch the live stream again and follow along, you can find it on NASA's channel. Just keep in mind that the time is still showing, so be sure to fast forward to where you want to look. Speaking of the live stream, how did they even manage to stream the impact? How did they communicate with a spacecraft hurtling toward an asteroid at 140,000 miles per hour? For most of the flight, DART communicated with NASA's Deep Space Network, a set of radio antennas around the world that allow us to talk to spacecraft out in the solar system. As DART got closer to Didymos, though, the signal began to get too weak to be useful. At some point, they switched over to using a 70-meter antenna in Australia to try to get a better signal. But eventually, that wasn't enough either. So how did they get the final images and data? Well, the answer is they didn't. the signal from DART to Earth was too weak to be usable once the spacecraft got within 400,000 miles of Didymos. After that, the last images were taken by DART's Didymos Reconnaissance and Asteroid Camera for Optical Navigation, or DRACO. Those images were then processed and sent back to Earth through the same optical navigation system that guided the spacecraft to the asteroid. As you can see, the last few days leading up to impact were pretty hectic for the DART team. So what happens now? Well, now the hard work begins. The team is going to sift through the massive amount of data they collected during the flight and try to use it to learn as much as possible about asteroids. More specifically, they want to understand how well they can predict the outcome of a future impact like this one. You know, just in case we need to do it for real sometime in the future. But how will they be able to do that when they don't have any data from the actual impact? Well, they do, kind of. You see, DART had a companion cube named LISA cube that was built by the Italian Space Agency, the National Research Council of Italy, and the University of Naples Federico II. It was designed to measure the dust released during the impact, and while it didn't manage to get any pictures of the collision itself, it did detect a cloud of dust expanding outwards from the point of impact. Now obviously, that's good news because it means that the impact actually released dust. But unfortunately, the camera's orientation meant that it couldn't see the main plume from the collision, so it doesn't tell us much about the composition of the asteroid or anything like that. What we really need are pictures of the crater left by the impact. And luckily, we have those. Sort of. The Japanese Space Agency's Destiny Plus spacecraft has been following DART since launch and managed to capture some images of the aftermath. But these aren't great because the lighting conditions weren't ideal. Basically, it was night on the asteroid. Luckily, though, we also have the Heritage Space Telescope, which is currently observing Didymos from Chile. And it managed to get a couple of pictures of the asteroid in better lighting conditions. These show the location of impact pretty clearly, but unfortunately it can't actually image the asteroid itself. It can only image the light reflected off of it. So the asteroid is just a bright spot in the photos. Over the coming weeks and months, though, researchers will use various telescopes around the world to continue imaging the asteroid. Eventually, they hope to map the surface to better understand the shape of the crater left by the impact. So that's what's happening now. And what's next? Well, NASA already has a list of asteroids they'd like to hit, with similar missions in the future. But for now, they're just going to focus on learning everything they can from this one. And thankfully for us, it was a resounding success.